All right, let's talk about something that's literally pressing down on you right this second. It's a force we feel every single day of our lives, but we almost never think about it. We're going to dive in and figure out exactly how we calculate atmospheric pressure.
So, to get us started, I want you to think about this question. It sounds kind of poetic, right? What is the weight of the sky? But here's the thing, it's not just a beautiful thought. It's a real question with a very real, measurable answer.
And nope, the answer isn't in some philosophy book, it's pure physics. For this whole explainer, we're going right to the source, a textbook on fluid mechanics. This is where the science is all laid out, and we're going to walk through it step by step. You see, when we ask about the weight of the sky, what physicists are really talking about is atmospheric pressure. It's this simple but kind of mind-blowing idea that the huge ocean of air above all of us actually has mass. And, because of gravity, all that mass is constantly pushing down on us. The easiest way to think about it is like this. Imagine you're diving deep into the ocean. You can feel the weight, the pressure of all that water above you, right? Well, the atmosphere works the exact same way. It's just a different kind of fluid, a massive column of air that stretches all the way up to space, pushing down on everything. Now, here's where it gets really cool. We don't just have to feel this pressure, we can actually calculate it with incredible accuracy. And to do that, we just need to unpack one core scientific equation. The official term, straight from our textbook, is hydrostatic pressure. It just means the pressure from a fluid, like our atmosphere, that isn't really moving around. It's just sitting there being pulled down by gravity. It's all in a state of balance, or equilibrium. And this brings us to the key that unlocks the whole thing. This is equation 4.16 from our textbook. Now, it might look a little complicated, but all it's saying is that the difference in pressure between two spots in a fluid is just the density of that fluid times gravity times the height difference. We're going to make it even simpler in just a second. Okay, let's break this down. For what we're doing, think about it like this. The pressure way out in the vacuum of space is basically zero, right? So if we set our starting point, that P0, at the very top of the atmosphere, we can pretty much just ignore it. That leaves us with a much friendlier formula. The pressure down here at the surface, P, is simply the density, rho, times gravity, G, times the total height of the air, H. That's it. That's the formula we need. So great, we have our formula, P equals rho GH. But this leads to a pretty big, pretty obvious problem. To use it, we need to know H, the height of that column of air, which brings up a huge question.
Yeah, exactly. I mean, think about it. The atmosphere doesn't just have a neat little lid on it, it just fades out into space. So how on earth are you supposed to get a number for H if you don't even know where the top of the column is?
And this is where the real genius kicks in. The solution was to just stop trying to measure the air directly. It's kind of unmeasurable. Instead, the brilliant idea was to measure the effect of the atmosphere's weight by balancing its force against something you can measure, like a column of a really dense liquid, like mercury.
And the person we have to thank for this incredible breakthrough is Evangelista Torricelli. As our textbook points out, he's the Italian physicist who, way back in the 17th century, invented the barometer, the very device that makes this whole thing possible.
Okay, so we've got the theory, we've got the history. Now let's put it all together. Let's see exactly how Torricelli's incredible invention lets us plug real numbers into that pressure equation. So how does this barometer thing actually work? It's amazingly simple. You take a glass tube, fill it with mercury, and then you flip it upside down into a dish that also has mercury in it. Now gravity is trying to pull the mercury out of the tube, but at the same time, the weight of the entire atmosphere is pushing down on the mercury in the dish, which forces it up into the tube. It's like a tug-of-war until everything reaches a perfect balance. And that height, the height of the mercury column once it's balanced, that is the magic number. We couldn't measure the height of the atmosphere, but we can easily take a ruler and measure this column of mercury. That gives us our H, and since we already know the density of mercury, that's our rho, and we know the force of gravity, that's G, we just plug those numbers into our simple formula, P equals rho GH, and boom, you've just calculated the weight of the sky. Now this is way more than just a clever old experiment. Understanding this one basic principle is absolutely critical in our modern world. The implications are just huge. I mean, just look at this. The textbook's prologue points out how this one idea is a cornerstone for all kinds of modern engineering. Aerospace engineers need it to design planes. Civil engineers need it to build dams that can hold back tons of water pressure. Mechanical, chemical engineers, they rely on this stuff every single day. It's everywhere.
And that really brings us to the final takeaway. Think about it. A little bit of mercury in a glass tube was enough to let us measure the weight of our entire atmosphere. It's just an amazing reminder of how simple, elegant tools can help us see and measure the huge invisible forces that shape our entire world. It just makes you wonder, what other invisible forces are out there, just waiting for the right tool to reveal them?